Hello guys, I hope you're good. I'm also fine. So today we'll be discussing integration of hyperbolic functions. So as you know, like this is similar to integration of trigonometric functions, so the same we're gonna solve it using the same explanation. So but I'll just do it, of course. So in integration of hyperbolic functions, we use the same procedure. So if you are integrating a hyperbolic sine of f of x, so f of x representing any argument, it could be x, could be x squared, it could be theta, whatever thing that you'll be dealing with. So for example, if for that case you are integrating the hyperbolic sine of f of x dx, so you need to make sure that here next to this hyperbolic sine of f of x, you need to make sure that there is the derivative of f of x. So f of x is the argument, or is the angle. In simple terms, I can say it's the angle. It's the angle for that one, because people use that language in most cases. So yeah, whatever that you have here, you should make sure that here, where there is f prime of x, you have the derivative of it. Make sense? So that's so after that is that, then you can conclude that if I have my f prime of x and the hyperbolic sine inverse of f of x is that, then you can conclude and say that is equivalent to hyperbolic cos of f of x plus c. But then I'll do examples, of course, to explain this nicely with the use of equations. So yeah, so there are a lot of formulas here which you are supposed to memorize for you to be able to answer questions, of course, since sometimes in your test you won't be given these formulas. So yeah, it's good to memorize them. All right, so let's start. Okay, so here's our first question. This question says integrate hyperbolic sine of 5x plus hyperbolic cos of 3x with respect to x, of course. So when we integrate this, so the first things that I can do is just to split them to avoid confusion. So I'm going to split them. So I'm going to split these two terms, this term and this term, for each to have its own integral. So this is going to be hyperbolic sine of 5x dx plus integral of hyperbolic cos of 3x, hyperbolic cos of 3x dx. So what I was saying is that before you conclude that this integral of hyperbolic sine is equivalent to that one of hyperbolic cos, you need to first make sure that here you have the derivative of the argument. So the argument for this case, it's 5x. So when we differentiate 5x with respect to x, what do we get? We get 5, right? So we don't have that 5 here. So we are not allowed to conclude that before we make sure that there is a 5 here, which is the derivative of this argument. So you're going to put that 5 here. So look, in our question, there was no 5 there initially. So, but now we have put 5 so that we can be able to answer this question. So remember, we're not trying to change our question. So if we just leave this 5 the way it is, that means we have changed the given question. So we need to make sure that we don't change the questions that are given. We answer them the way they are. So what we need to do is just to cancel out this 5 by multiplying by 1 over 5, so that this 5 that is inside the integral can cancel this one outside the integral. The same explanation applies to this one. Before we conclude that the integral for this hyperbolic cos of x is equivalent to that one of hyperbolic sine, then we need to first make sure that here next to this hyperbolic cos we have the derivative of this argument, which is 3x. So when we differentiate 3x with respect to x, what do we get? We get a 3. So we need to make sure that here there is a 3, and then after that you cancel out that 3 by multiplying by 1 over 3, so that the 3 and 3 cancel out, and then you go back to the same equation. However, we're not going to cancel out because of we want to make use of f prime of x and f of x, you understand? So we know from the formulas, if we have f prime of f of x and f prime of x, then we can then conclude that this it is this formula of hyperbolic cos of x, understand, or cos of f of x for that case. So alternatively, or I basically in most cases I use the formulas of course, but not directly. So in most cases I answer these questions in the following manner, which is the method that I advise. So look, this is what I do. So after you have manipulated the constants there so that you have the derivative of the argument, so this is what you do. You ask yourself, what is it that was differentiated for you to get positive hyperbolic sign? So you ask yourself, the thing that was differentiated for me to get positive hyperbolic sign is what? It's hyperbolic cos, right? So then after that, you make sure that whatever that's outside the integral goes with you to the answer. So you take that 1 over 5 with you to the answer. So it's going to be 1 over 5. And then you say the thing that was differentiated for you to get a positive hyperbolic sign, it's what? It's positive hyperbolic cos. So it's positive hyperbolic cos of 5x. Then the same explanation goes to this one. If we have the derivative of the argument and this hyperbolic sign, then we just then ask ourselves, what is it that was differentiated for us to get this positive hyperbolic cos? Then it's positive hyperbolic sign, right? Then of course whatever that's outside the integral should go with you to the answer there. So that 1 over 3 will go with you to the answer. It's going to be 1 over 3 hyperbolic sine of 3x, then plus c. Then tada, you have your answer. So why am I answering these questions in this following manner? So of course I'm assuming that you understand if of course you checked my previous videos whereby I was explaining integration of trigonometric functions, then you'll understand why I mean. But of course I'm gonna re-explain it again here. So look, remember, integration, it's us going back to what was differentiated before. You understand? It's more like we are given an answer, then they say find out. It's more like we're given an answer which is differentiated, or something that is differentiated. Then now we're trying to find out how it was before it got differentiated. So hence, when I'm answering this question, I'm saying, what is it that was differentiated for me to get this? Because in integration, inside an integral, you're given something that was differentiated. You understand? So you need to then ask yourself that, what is it that was differentiated for me to get this thing that is inside the integral? Hence, when I'm answering this question, I ask myself, what is it that was differentiated for me to get whatever that I have there? You understand? So of course, if you have already crammed your formulas for differentiation, then you don't really need to cram some of the formulas for integration. You can just like work them out like that through asking yourself that what is it that was differentiated before, and then easy like that. Makes sense? All right, so I have to also let you know that you're not only gonna work with or in your test, it's not gonna be direct. You see, this question was very direct. You can see that, all right, I'm just applying inverse hyperbolic functions, like integration of integration of hyperbolic functions, I mean. So it won't be direct sometimes, more especially in your test, so that you don't get good grades. You know, sometimes they fight you, these lecturers or the examiners. So what you need to be aware of is that sometimes you will meet general power rule inside the process of solving these integration of hyperbolic functions, just like the question presented here. As you can see, when you check this question, you can't say that something was differentiated for you to just get hyperbolic sine squared multiplied by hyperbolic cos squared. It's not there. It's not there in the formula. So hence I'm saying it's there. Then you need to apply other rules. Just like general power rule for this case is the one that's gonna work for you, or what? No, general power rule is the only one that's gonna work for this case. So what we need to do is just to rewrite it nice. Of course it's nice, but let's write it more in a nicer way. So what are we gonna do here? We can see that we can just say this is hyperbolic sine of x squared multiplied by hyperbolic cos of x, and then what? Dx. So of course we can always also go back to the questions that I always tell you that these are the questions that we use whenever we are answering questions. The first question is that you ask yourself, can I simplify the given integral? So when you check, is there something that you can do here in this integral? Maybe change cos to something else, and then some certain things cancel each other, or perhaps change this hyperbolic sine squared to something else, and then things cancel each other, and then at the end of the day you end up having maybe one hyperbolic function. Then from there you integrate it. So you ask yourself, so after you have asked yourself, you realize that even if I change this one using the square identities, then still I will be stuck with what is this? Something like this again. So that means that rule won't work, or that's basically simplifying won't work. That's what I'm trying to say. So then the second question that you need to ask yourself is that, can I make one f of x and the other one be f prime of x? Why are we doing this is to try to use a general power rule or general log rule. So when you ask yourself here that, can I make maybe hyperbolic cos of x to be my f of x, will it work? Will hyperbolic sine of x squared become f prime of this? Then definitely no. But how about if you rewrite this thing nicely like this? Then you make hyperbolic sine of x to be your f of x, and then hyperbolic cos of x to be your will hyperbolic cos of x be f prime of x? That's what I'm trying to say. So then you'll see that of course this could work because of definitely when we differentiate hyperbolic sine of x, then hyperbolic cos of x becomes the derivative of this. And general power rule states that if we have f prime of x to the power n and f prime of x here, then we can then conclude that our answer for that integral that we're dealing with is just, you take your f of x. So for this case, our f of x is just hyperbolic sine. It's just going to be hyperbolic sine of x to the power of, so it's going to be n plus 1, so it's going to be 2 plus 1, which is just going to be 3 divided by 3 plus c. Then tada, you have your answer. So easy busy. So that's how it's supposed to be done. So yeah, and then we've got this type as well. All right, so this one you need to memorize it in this following manner. Whenever we have one hyperbolic sine, or one hyperbolic cos, and it has to the power or its power to the it has a power of an even number. You understand? That's what I'm trying to say. So whenever we have one hyperbolic sine and it has an even power, then we need to use what is that, half angle identities, for you to be able to integrate that one. You understand? So that we can get rid of the squared. So we are substituting with half angle identities of of hyperbolic functions. Yo, the terms in here, yo, I'm sorry guys, you can see it's like I'm stammering because it's just the terms, guys. Yo, hyper, what, blah, yo, it's a lot, guys. It's easier when you're just writing, you know, but now when it's like, it's time to explain, yo, now hyperbolic in your mind, something else, have you. But okay, sorry for that. Anyway, I was saying that you need to memorize that. Let's take if it's cosh squared or sinh squared, you need to know that you need to cram that I need to substitute half angle identity so that I can get rid of the squares, because there is nothing that was ever differentiated for me to get sine squared or cosh squared, you understand? So that's the reason why we are substituting by half angle identities. So that's what we're gonna do. So for this one, that's what I'm gonna do. We're gonna substitute it by 1 over 2 multiplied by hyperbolic cos of 4x. For this case, remember we double the angle, so it's gonna be 4x minus 1 and then dx. Remember, whenever we are writing the half angle identities, when in here it must be the double angle of that one. So if here is 2x, then here it must be 4x. If it was just x, here it was gonna be 2x. So then from there I can split and make each to have its own integral here. That means I'll end up having 1 over 2 integral of cosh 4x, or hyperbolic cos of x, minus 1 over 2 integral of 1 dx. So what did I do? I multiplied both this term and that term by 1 over 2 and then also made each term to have its own integral. So that's what happened. So now we need to integrate this one. So what we need to first make sure is that next to this hyperbolic function we have the derivative of our angle. So this angle is 4x. When we differentiate 4x with respect to x, what do we get? We get 4. So I'm gonna put that 4 because it's supposed to be there for our rule to work, for us to be able to apply that rule. So now when we have the derivative of the argument, we need to make sure that since this 4 was not here, we need to cancel it out by multiplying by 1 over 4 outside the integral. So I'm going to multiply by 1 over 4 outside the integral so that the 4 and the 4 can cancel out. Makes sense, right? Yeah. And then from there, you ask yourself, what is it that was differentiated for you to get positive hyperbolic cos of x, or 4x for this case? So when you ask yourself, you'll realize that, okay, it's positive hyperbolic sine of 4x that was differentiated for me to get this positive hyperbolic cos of that, right? So then you conclude whatever that's outside the integral should always go with you to the answer. So that's going to be 1 over 2 multiplied by 1 over 4. It's the same as 1 over 8 multiplied by hyperbolic sine of 4x minus 1 over 2. Integral of 1 is just x, right? Then plus c. Then ta-da, you have your answer. So just like that. So that's how we answer these questions. Make sense, right? It should make some sense, of course. All right. So let's see. All right, okay, let me go back to these formulas. What you're gonna realize from these formulas is that there is no standard rule for differentiate or for integrating sec of f of x. Like what I'm trying to say is this: integral of sec of, there is no rule that says there is no rule for integrating this one, hyperbolic sec of f of x. dx. You understand? Also, there is no rule for integrating this one, hyperbolic cosec. So if we have cosec of f of x dx, there is no direct rule for you to integrate this one as well as this one. So we need to know that there is a special way for you to be able to integrate them, because there are questions whereby you'll be asked to just integrate this one. So you need to know that it's possible for you to integrate it. Makes sense, right? So now that's what we'll be dealing with. So stay tuned. Stay tuned. Stay tuned. Okay, here's the question. Here is the question. All right, you can see that we've got what is this? Integrate the following. So that's the question. And then number one, it says integrate hyperbolic sec of x dx. So the procedure is as follows. It will never change. So if you cram it once, you are secured for the rest of your life. It will never change. It will never change. If it changes, then I don't know, but it will never change. I promise you. So you just need to memorize it or cram it. Basically cram it, because as students, that's what we do. That's what we do. We cram. There is no way you can convince me that you know these things, because after few days you don't even know how to solve them. So it's cram work. So do the cramming like you do always. Anyway, let's continue. So what is this? So this is the procedure. So the first thing first, whenever you're integrating hyperbolic sec of x dx, then you need to rewrite it first into its equivalence when it comes to reciprocal. So this is going to be 1 over hyperbolic cos, right? So this one going to be equivalent to 1 over hyperbolic cos of x dx. Then second step, you multiply by 1. Second step, you multiply by 1. And that 1 should just be whatever that you have on the denominator. So here it's hyperbolic cos of x. So that means when we multiply by our 1 here, it's going to be as follows. It's going to be 1 over hyperbolic cos of x multiplied by, so now we're multiplying by 1. So this is going to be hyperbolic cos of x divided by hyperbolic cos of x multiplied by dx. So it's a 1 because of hyperbolic cos of x divided by hyperbolic cos of x gives you a 1. Hence I was saying you multiply by 1. Makes sense, right? So yeah, I hope you're not confused. I'm not here to confuse you, but to make you see light at the end of the tunnel. Anyway, so from here, you multiply the numerator and the numerator, and then also the denominator multiplies the denominator. So at the end of the day, we'll have hyperbolic cos of x divided by what? By hyperbolic cos of x squared, just like that. Dx. You understand? Then from here, you substitute hyperbolic cos of x squared into its equivalence when it comes to square identities. When it comes to square identities, remember, hyperbolic cos of x squared minus hyperbolic squared of x it is equivalent to 1. So if you try to make hyperbolic squared of x hyperbolic cos of x squared the subset of the formula, then you'll realize that that is equivalent to 1 plus hyperbolic sine of x squared, just like that. I hope I'm saying it correctly, but hey, I doubt. The terms, guys, you can also see or you can also hear that it's not easy. All right, but anyway, what I was saying is that now we're going to substitute this one into its equivalence when it comes to the square identity. So that is equivalent to 1 plus hyperbolic sine of x squared. Okay, everything is squared there. Then dx. So this is what I was saying. So first thing first, whenever you're integrating hyperbolic sec of x dx, you substitute hyperbolic sec of x to its equivalence when it comes to reciprocals, and that becomes 1 over cos, and then you multiply by 1. That 1 becomes whatever that's in the denominator, you multiply by it, like denominator over the numerator over the yeah, you understand. And then you multiply the numerator and the numerator, denominator and the denominator. And then from there, you then substitute this hyperbolic cos of x squared by its equivalence when it comes to square identities. So then this becomes this. Then from there, now it will be easier for you to integrate this. So when we analyze this, we check. Definitely there is nothing that was ever integrated for us to get what, something like this. Of course, basically it's there. It's there. Let me not say it like that. What can I say is that or maybe from your formulas, let me say from your formulas of what, of hyperbolic functions, whenever we differentiate, there is no way something was differentiated for us to get this fraction. You know that, yeah, that's basically what I was trying to say. So what does that tell you? It tells you that now for you to be able to integrate this fraction, you then need to use other methods. So I've explained nicely this method when I was doing, I don't know, it's video 3, I don't know, I forgot, activity 3 there under integration. So you could go backwards sometimes to check all of the skills involved whenever we're integrating a quotient or a fraction, you know. So you'll see some of them there, of course. So you have seen that, okay, there is no way I can say maybe, okay, hyperbolic tan was differentiated for me to get this fraction. So what do you then do? You then ask yourself, can you simplify this? Can you maybe substitute something and then things cancel out? And then nah, you can't do that. Otherwise, if you do it, you'll go back to what, a hyperbolic sec, and you don't want to go back there, because that's the only simplification you can make. You can just say 1 plus this is equals to cos squared, then what, this and this cancel out, and then you go back there, and then back to 0. So now you need to take it from here and you go forward. You understand? You're not supposed to go back. So you ask yourself, so since I can't simplify, then can I make one f of x and the other one f prime of x? You check. If I make this, the numerator, to be f of x, can this be f prime of x? Definitely no. We can't say when we differentiate cosh we get 1 plus something. There is no way. There is no way. Okay, so then we check. What if we let the whole denominator to be f prime of x? F of x, I mean, can the numerator be f prime of x? No, because of when we differentiate this one, we're going to get 2 hyperbolic sine of x multiplied by hyperbolic cos of x, you know. So it's not going to work. So what do we then do? We need to then rewrite this nicely. Rewrite it nicely again, because it's a fraction, you know. So this is going to be hyperbolic cos of x divided by 1 plus hyperbolic sine of x, and then dx. So now I'm trying to see if I rewrite it in this way, and then I make only the thing that is squared there, or I only try to make a hyperbolic sine of x to be my f of x instead. So when I make this one to be f of x, can the numerator be f prime of x? Yes. And then this structure of having f prime of x divided by 1 plus f of x squared is what? Is the one for tan inverse, you know. So so then this tells us that the answer for this is just going to be hyperbolic tan inverse. Oh no, it's just tan inverse, or not hyperbolic tan. It's just tan inverse of what? Of this argument, which is hyperbolic sine of x. So that's going to be hyperbolic sine of x, and then plus c. So that's just it. That's just it for that one. I don't know. So yeah, please memorize that one, and then you can also do the same. Do the one for hyperbolic cosec as well, and then using the same procedure, you should be able to get the same answer, provided that you first make the reciprocal, and then change multiply the numerator and denominator and denominator after multiplying by 1, of course, and then you change using the same procedure. You should be able to reach to the correct answer when you solve that one of cosec, hyperbolic cosec, you know. So guys, so now in this question, sometimes you will be solving product, you'll be solving the product of an exponential function and a hyperbolic function. So you need to know that we use the following procedure. So I'm gonna use this question to explain what I'm trying to say. So what you need to know is that whenever we have a hyperbolic function and an exponential function, we do the following procedure. You substitute the hyperbolic function by its equivalence, or by the definition of hyperbolic functions. We know that hyperbolic cos of x is the same as e to the power x plus e to the power negative x all over 2. So that's what we do whenever we're integrating an exponential function and a hyperbolic function. Yeah, it has to be an integration. Okay, makes sense, right? So yeah, so that's what we do. So that means our first step here should be to first change our hyperbolic function there. So that's going to be e to the power x plus e to the power negative x divided by 2 dx. So you need to know that the exponents of these is always just whatever argument that we have here, you know. So this one, of course, it must be negative argument, positive argument, you know. So if we had 2x here, then it was supposed to be e to the power 2x, e to the power negative 2x. If it was x squared, e to the power x squared plus e to the power negative x squared. So the exponents of this are dependent on the argument of that hyperbolic function. Makes sense. Then from here, we're going to just multiply these two terms. So when you multiply, you'll just add the exponents, of course. So this is going to be, we can take the 2 out. So this is going to be 1 over 2. I've taken it out. I hope that doesn't confuse anyone. So this is going to be e to the power 2x. How did I get it? I multiplied this e to the power x multiplied by this one. Whenever you multiply the powers of the same base, you add the exponents. So x and x, they add each other to become 2x. Then plus e to the power x multiplied by that is just going to be e to the power 0, which is the same as 1, right? And then you integrate this with respect to x. So this is going to be what? This will then be so now we're integrating now, right? Or maybe I can first split to make things easier. Yeah, let me first split to make things easier. So this is going to be e to the power 2x dx plus 1 over 2 integral of 1 dx. So what did I do? I split it. I made each and every term, since we had 2 terms, to have each and every so I made each and every term here to have its own integral sign, you understand, so that I can safely use the rule that I want to use here. So now we go back to integrating exponential functions. Whenever we're integrating an exponential function, we need to make sure that next to this exponential function there is the derivative of what? Of the exponent. So the derivative of 2x, what is it? It's 2, right? So for this case, we're gonna write that 2. So this 2 was not given to us in the question. So what do? We need to cancel it out by multiplying by 1 over 2 here outside the integral. So that this 2 and this 2 can cancel out. This 1 over 2 is coming from there, whereby it was the time whereby we haven't done anything to the question, but now we're trying to do something to it. So we are introducing another 1 over 2, you understand, which is there to cancel out this 2 which is inside the integral. Makes sense, right? So whenever you have an exponential function e and the derivative of it next to it, and you're integrating this thing, then you can then conclude that the thing that was differentiated for us to get this, which is the derivative of the exponent multiplied by this exponential function, it was just e to the power 2x. And then of course we shouldn't forget whatever that's outside the integral to go with us to our answer. So we're gonna have 1 over 4 plus 1 over 2 integral of 1 it's just x, guys. So it's just gonna be 1 over 2. It's just gonna be 1 over 2 multiplied by x plus c. Then that's it. You have your answer. So if you have already forgotten how to integrate exponential functions, kindly feel free to go back to my previous videos. You'll see activity what I think it's activity 4, integration of exponential functions. You will learn more there. I've explained clearly. I don't have to go back here because I've made a video about that then. So yeah, please, you just do that. So that's just it. So now we'll just solve different questions that involves all of these techniques. So yeah, stay tuned and be ready to write there. Be ready to write. Be ready to write. Okay, here's our question. So under activity 7 now, the first question says integrate the following: integral of x squared, hyperbolic sine of x cubed dx. You understand? So what are we doing here? We're integrating. So guys, for you to be able to learn this quickly, you need to also be writing, writing there. So stop cruising. Now it's about time you also do these questions on your own. So feel free to pause this video, attempt this question on your own, and then resume the question just after a few seconds to see how I've done it. Of course, I'm hoping that we're gonna get to the same answer, provided that you don't make mistakes. I don't do mistakes, of course. All right, so what are we supposed to do? First thing first, whenever you're integrating an hyperbolic function, you need to make sure that next to this hyperbolic function, you have the derivative of what? Of the argument. So if here you have x cubed, that means here I'm expecting to have the derivative of x cubed. So that's what we're gonna do. So this is how it's gonna happen. I'm gonna rewrite this nicely. Hyperbolic sine of x cubed dx. So when I differentiate I can see that this can be the derivative of this. However, it's not complete because of whenever I differentiate x cubed, I get 3x squared. So I only have x squared, and I know that I'm allowed to cook what? Constants, right? So I'm just gonna put like my 3 here so that this thing can fully be the derivative of the argument. So then also Since I didn't have these 3, I need to make sure I cancel it out by multiplying by 1 over 3. So I'm going to multiply by 1 over 3 outside the integral so that the 3 and 3 can cancel out. Then from there, you ask yourself, what is it that was differentiated for you to get a positive, because it's positive here. It's positive hyperbolic what? Sine of x cubed. So you answer yourself that it is a positive hyperbolic cos that was differentiated for you to get whatever that we have there. Makes sense, right? All right. Since it does make some sense, then you need to just remember that whatever that's outside the integral goes with you to the answer. So that's going to be 1 over 3 hyperbolic cos of x cubed for this case, then plus c. Then ta-da, you have your answer. Easy, 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 easy. So I hope you got the same answer as well, because you can't afford to be getting incorrect answers, guys. It's very expensive. It's very, very, very expensive. So please, if you're not rich, don't do that. Don't do that. It's very, very expensive. I know. All right, so now we have another question. Please give it a try. Of course, these easy ones won't come to the test. You will get the complicated ones. You'll see the complicated ones as we go down. All right, so what are we supposed to do? We just need to first make sure that next to this hyperbolic sign, we have the derivative of the argument. Yeah, so that means that we're gonna rewrite this nicely and say and say this is hyperbolic sine of x over 2 dx. So whenever we differentiate x over 2, what do we get? We get 1 over 2. So you should make sure that here you have the derivative of the argument. You understand? So since our argument was x over 2, here we should have 1 over 2, which is the derivative of x over 2. And then because of we didn't have 1 over 2, you need to cancel it out by multiplying by what? By 2 outside the integral, so that the 2 and 2 can cancel out. Now when you have the derivative of the argument and this hyperbolic function, you then ask yourself, what is it that was differentiated for me to get this hyperbolic positive hyperbolic sine of x over 2? Since I now have the derivative of that, then you just ask yourself that question, and then you will realize that it is hyperbolic cos that was differentiated for you to get that one. So whatever that's outside the integral always goes with you to the answer. So it's going to be 2 hyperbolic cos of x over 2, then plus c. Ta-da! You have your answer for that question. So yeah, that's just it. It's very easy, right? So I hope you got it, guys, because remember, whatever question that I'm doing now, you are supposed to be posting the video before you see how I've done it. And then yeah, that will be it. And then we have another question here. It's what? It's integral of hyperbolic sec of 2x minus 1 squared dx. So you ask yourself, is there something that was ever differentiated for me to get sec squared first? A hyperbolic sec of something squared is there. Yeah, it's there, of course, right? It's there, right? So that means for us to be able to integrate this, we only need to just make sure that we have the derivative of the argument next to this hyperbolic function, right? So yeah, that's what we're gonna do. So let's rewrite this nicely first. So when we differentiate 2x minus 1, what do we get? We get just, before that, let me just rewrite the equation first. Hyperbolic sec squared of 2x minus 1 dx. So whenever we differentiate 2x minus 1, what do we get? We get just a 2, right? So remember, that's the procedure for integrating hyperbolic functions, you need to first make sure that next to that trig function you have the derivative of the argument. So the argument for this case is 2x minus 1. When we differentiate 2x minus 1, we get 2. So this 2 was not given to us in the question. So what do we do to it? We cancel it out by multiplying by 1 over 2, so that the 2 and the 2 can cancel out, and then we go back to whatever question that we're given. But we're not going to cancel anything out. We're going to make use of the derivative and the and this hyperbolic function together with its argument there. So then we ask yourself, what is it that was differentiated for us to get positive hyperbolic sec squared? You understand? So when you ask yourself that question, you'll realize that, oh, it's just a hyperbolic term that was differentiated for me to get hyperbolic sec squared. So whatever that's outside the integral always goes with you to the answer. So that 1 over 2 will go with you. Then the answer to that thing of what is it that was differentiated, you write it there. So it's going to be a hyperbolic tan of 2x minus 1. Then what? Plus c, right? Then ta-da, you have your answer. What else do you need? Easy that one. It won't come. The ones that are gonna come are like these ones. Okay, so this one, it's also easy. It shouldn't trick us. Okay, so we have integral of hyperbolic sine of x divided by 1 plus hyperbolic cos of x dx. So when we check, is there something like maybe hyperbolic cot that was differentiated for us to get a fraction? No. Then what do? We need to use another method. So we first check, then can we simplify this? You look at it, you analyze it, and then you conclude. You say, no, I can't do anything to this question. I can't. Or if I can, or maybe change 1 to its equivalence when it comes to square identities, will it help you? No, it won't help you in a way of answering this question. Remember, whatever method of simplifying or whatever skill or whatever way that you're going to use to simplify should be a way that will help you to integrate at the end of the day. You can't just say, okay, I can change this one to become hyperbolic cos squared minus hyperbolic sine squared, and then at the end of the day it doesn't help you. Why are you even doing it? You can't do such a thing. So immediately when you can see that, nah, I can't simplify this, then you need to check the following question, which states that can I make one f of x and the other one f prime of x? So you check, can I make this numerator to be f of x, and then this thing is just gonna be my f prime of x? You check, when I differentiate hyperbolic sine, I don't get 1 plus, so that means it's failing. And then what if I make the denominator then to be f of x? Can that one be f prime of x? You differentiate this, you see. So if I differentiate 1, it's going to be 0. If I differentiate hyperbolic cos, I get hyperbolic sine of x. Then what does it mean? It means that I can use general log rule because of my f of x is in the denominator, also because of that f of x has an exponent of n. Remember, what I'm trying to say is this thing has an exponent of 1. So whenever our f of x is in the denominator and it has the exponent 1, then we're using general log rule. If you forgot this, feel free to go back to my previous videos. You will see what I'm talking about. You will remind yourself. Of course, everyone forgets. Even me, I forget these things. But yeah, what can we do? It's maths. It's not nice. So yeah. So if this can be f of x, then that one becomes f prime of x. Then we can just use general power rule, like I said. Then we will then conclude and say that's just natural log of 1 plus hyperbolic cos of x. Then plus c. Ta-da! You have your answer. Easy, right? Easy, 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 easy. Yeah. Yeah, it's easy, guys. It's easy. You are right. It's very easy. Okay, this one can be done in about three ways, I think. All three ways are correct. Which way should I then do? It's you asking me now. Let me analyze your brain there. It seems like you're tired. You're saying, just do one, man. Okay, let me just show you three of them then, just to flex. Sometimes you need to flex. Okay, so this one, this type of question whereby you have hyperbolic sine of x multiplied by cos of x dx, it can be done in three ways or a lot of ways. Okay, why am I saying it can be done in a lot of ways? Of course, when we check this one, we can't say that we can't say that from our formulas we know that when we differentiate maybe sine, hyperbolic sine, we get hyperbolic sine multiplied by hyperbolic cos. So you can't then conclude. That means that also tells you that no, this one is not direct. That means it wants those other methods. Maybe your general power rule or any other thing. So you first check, can I simplify this, maybe substitute this, and then certain things cancel out? No. So what do you then do? You ask yourself, can I make one f of x and the other one okay, so basically I shouldn't have said no, because of course we can simplify this, we can rewrite this in a simple way. I shouldn't have said that though. Why you I don't know how I said no, although I said that this question could be solved in a lot of ways, and in my mind I know that I had already included that way of simplifying. So of course we can simplify this. All right, so let's start with the simplifying way. All right, so let's start with the simplifying way. So when you simplify it, it's gonna be like this. So we're gonna force this to become the double angle of hyperbolic sine. All right, so we're gonna multiply this by 1 over 2 multiplied by 2, then hyperbolic sine of x multiplied by hyperbolic cos of x dx. You understand? So what did I do here? I multiply by 1. So 1 over 2 multiplied by 2, it's a 1. A 1 that I had here in my answer. So I have 1, 1. But then I can make use of 2 hyperbolic sine of x, hyperbolic cos of x. You understand? That's going to be the double angle. So I'm going to take this 1 over 2 outside the integral, and then I'll be left with, if I change 2 hyperbolic sine of x, hyperbolic cos of x dx, then I'm gonna have what? That's the double angle, right? So the double angle, that one is the double angle of sine. That's what I'm trying to say. So that's going to be the hyperbolic sine of 2x dx, like this. And then what? So now I only have one hyperbolic function. For me to integrate this, it's easy. It's easy. Why? Because I only need to make sure that next to this hyperbolic function, I have the derivative of the argument. The argument is the angle, of course. So this argument, when I differentiate it with respect to x, what do I get? I get 2, right? So I only need to make sure that I have 2 here. And then when I have 2, I just multiply this this integral by what? By 1 over 2. So initially we had 1 over 2 outside the integral. So now I'm putting 1 over 2 again, so that this 1 over 2 can cancel out these 2, But then I'm not going to cancel out. I'm going to make use of it being like this. So if I have the derivative of the argument and also one one hyperbolic function, what do I then do? I ask myself, what is it that was differentiated for me to get positive hyperbolic sine? So it's hyperbolic cos, right? So whatever that's outside the integral should go with me to the answer. So that means I'll have 1 over 4, what? 1 over 4 hyperbolic cos of what? Of 2x. Then what? Plus c. Then that's it. You are done with that question. You are definitely done. Makes sense, right? It makes sense. I'm hoping so. All right, yeah. Of course, you can always differentiate your answer to say if you'll go back to whatever that was given there in your question to verify the answers. All right, let me just quickly do the other method that I was talking about here, because now this video is getting long. All right. So what I was saying is that alternatively, one could use the following method: hyperbolic sine of x, hyperbolic cos of x dx. So one could say I want to make one f of x and one f prime of x. Why would one have thought of that? One would have thought of that because of one might not have seen that here you can simplify this, and fortunately it was still possible to solve this question even if you missed the simplifying part. So that's how someone would have gotten to this extent. All right. So you are going to make one. So here you can see that both of them, they agree to be f of x and making the other one to be f prime of x. So if the first thing first, I make hyperbolic sine of x to be my f of x, then that hyperbolic cos is going to be my f prime of x. You understand? So when I do this, then if I have f of x and f prime of x and then f of x to the power n, which is not equivalent to -1, then I can use general power rule. So that's just going to be, then the answer for this is just going to be hyperbolic sine of x, then you add 1 to the exponent, so that's going to be 2 divided by 2 plus c. Alternatively, one could have said, no, I want to make cos, I don't want to make that one subject of the, I don't want to make that one f of x, but instead I want to make cos to be the the f of x. So this is going to be hyperbolic cos of x dx. So what is one doing here? One is making cos to be the f of x. So if this is f of x, of course this is going to be f prime of x. So we don't have to do anything here. You're just gonna say that you're just going to apply general power rule. General power rule says that if you have f of x and f prime of x, then you just take your f of x, you add exponent 1 to it and divide it by n plus 1. So that's basically what we're doing. It's easy like that. And then 2 divided by 2 plus c. Ta-da! You are done. All of these answers, they look different, but they are the same answers. You can differentiate them if you want. You'll see that you'll go back to the same thing. Hence, I always repeat that you can have 3 different answers for one integral question, and all of those answers will be the same, or will be the correct answers for that particular question that you're dealing with. So that's just integration. Makes sense, right? So yeah. Anyway, let's quickly continue. That was just me trying to show you how you can solve that one. All right. Now we have this guy here. Let's see what damage we can do to him, because it's all about damage, you know. Okay. Now we have got this. You can see that, is there something that was ever differentiated for you to get hyperbolic cosec multiplied by hyperbolic cot? Yes, there is something that was once differentiated, or there is something that we know that when we differentiate it, we get hyperbolic cosec multiplied by hyperbolic cot, you know. So since we know that, we just need to first make sure, before we conclude, we need to make sure that next to these two hyperbolic function, we have the derivative of the argument. So the argument for this case is just 2x, is just 2x, you know. So we need to make sure that we rewrite this nicely. So this is going to be hyperbolic cosec of 2x multiplied by hyperbolic cot of 2x dx. So what are we supposed to do? We're supposed to make sure that next to these three hyperbolic function, we have the derivative of the argument. So the argument is 2x. When we differentiate 2x with respect to x, what do we get? We get a 2. So that 2, you write it there next to that. But because of you were not given this 2, what do you do to it? You cancel it out by multiplying by 1 over 2 outside the integral, so that the 2 and the 2 can cancel out. Makes sense, right? So from there, you then conclude and ask yourself, what is it that was really differentiated for me to get positive hyperbolic cos multiplied by hyperbolic cot? You understand? So what is it? You will find that it's what? It's negative negative what? Negative hyperbolic cosec. You understand? So negative hyperbolic cosec was differentiated for us to get the positive one. You understand? So it's going to be, so whatever that's outside the integral should go with you to the answer. And then that one, we say it's negative hyperbolic cosec of what? Of that argument that we're dealing with, 10 plus c. Ta-da! You have your answer there. So that's just it, NJ. That's how we do it. That's how we do it. Okay. All right. Now we have what? We have a hyperbolic tan squared of 3x dx. Hyperbolic tan squared of 3x dx. So what do we then do? We ask ourselves, is there something that was ever differentiated for us to get tan squared? Is it possible that way? No, it's not, right? Because there is no way we can ever differentiate something we get tan squared. So that means before we do anything to this question, we need to simplify it, rewrite it in a way that it can be integrated. So that means we're trying to simplify this thing. So we know that tan squared is equivalent, or hyperbolic tan squared is equivalent to what when it comes to the the hyperbolic functions, right? Like the square identities of hyperbolic functions, right? We know that this thing is the same as 1 minus hyperbolic sec squared of 3x dx. You understand? Why did I substitute this? Is because of there is nothing that was ever differentiated for me to get hyperbolic tan squared. So I then had to rewrite this thing in a way that I can have something that I can conclude that, okay, this was differentiated for me to get this. You understand? So yeah, so that's what happened. So then from here I can split this for each to have its own integral sign. So this is going to be negative integral of hyperbolic sec squared of 3x dx. So what's happening here? Okay, we can see that the integral of 1 is just going to be x, right? Integral of 1 is just going to be x. That's true. So, okay, let's analyze this one. So this one, what's going to happen here is that before we integrate this, we need to first make sure that we have the derivative of what? Of the argument. So the argument is 3x. So when we differentiate the x, 3x, what do we get? We get 3. But I didn't have this 3, so I need to cancel it out by multiplying by 1 over 3. So that the 3 and 3 cancel out. Then you then ask yourself, what is it that was differentiated for you to get positive hyperbolic sec squared? It's what? It's positive hyperbolic term, right? So whatever that's outside the integral, you take it with you to the answer. So that means here I'm gonna write minus 1 over 3 hyperbolic tan of what? Of 3x plus c. Then you are done. Just like that, you are done. And then now let's quickly see if we can solve another question. Guys, remember that you have to pause these videos and then be attempting these questions on your own as well as on the other side. Because if you don't do that, you are not gonna grab these things in a fast way, and you're supposed to grab them fast as you can. Okay, now we've got this type of questions whereby we have an exponential function which multiplies a hyperbolic functions. What do? We change the hyperbolic function to its equivalence when it comes to its definition. So what's going to happen here is that we're going to have this e to the power of 3x which multiplies. So we're going to change this one to its definition, which is just going to be e to the power 2x. You see, guys, I've already explained like all the type of questions prior to this. Now we're just cruising. We know that when we have this like this, then you just do this. So yeah, that's what's happening basically. So that's what's happening. E to the power 2x. It's a plus 1 for cos, right? So it's going to be e to the power minus 2x divided by a 2. Then dx. Then from here, we're going to take this 2 out. This 2 that's here, we're going to take it out. So it's going to become 1 over 2 outside there. I hope you are not confused. You cannot get confused by that one. That's easy algebra. And then from here, we'll multiply this and this. We'll make sure that this e to the power 3x multiply both these two terms inside the brackets. So that's going to be just e to the power of 5x plus e to the power of x and then dx. How did I get e to the power 5x? So this is 5x. I didn't write it nicely. Now it's looking like a 6. Okay, so this is e to the power 5x. Well, how did I get it? I multiplied this and this. So whenever we multiply powers of the same base, we add the exponent. So 3x plus 3x plus 2x gives us 5x. And then 3x minus 2x gives us positive x. Then from here, we can decide to split, of course, split so that each and every exponential function there, or each and every term has its own its own integral sign. So this is going to be e to the power of 5x dx plus 1 over 2 integral of e to the power x dx. Then from there, we integrate from here. So we can see that we're integrating an exponential function. The explanation of integrating an exponential function is that we need to make sure that next to this exponential function, we have the derivative of the exponent. So if this exponent is 5x, and we know that when we differentiate it, we get what? We get 5. So we need to make sure that here we have 5, right? And then we cancel out this 5 by multiplying by 1 over 5 outside there, because this 5 was not given to us. Now we're just putting it so that we can be able to answer this question. So whenever we have an exponential function e together with the derivative of the exponent, then we can then conclude that the thing that was differentiated was just that exponential function. Of course, we shouldn't forget to take whatever that was outside the integral with us to our answer. So that's going to be 1 over 10, because it's 1 over 5 multiplied by 1 over 2 there. That gives us 1 over 10, and then e to the power of 5x plus 1 over 2 e to the power x plus c. Then you're done. I hope you got the same answer as well. So it's very easy. It's very easy like that. It's nothing complicated. There's nothing complicated. All right. Here's another one. I hope you are pausing the video where you are so that you can work these questions on your own, like I've explained many more times. All right. So when we check this question, is there something that was ever differentiated for us to get tan squared multiplied by sec squared? No. So it tells you that you need to use another method. It's either general power rule or general log rule, or maybe trying to simplify those things. So we're going to start with simplifying. So when we check, if ever we're going to try to simplify this question, was it going to work? Like maybe changing, I don't know, tan squared to something else? Will it work, or will it help us? Basically, working, I mean, will it help us to answer this question? Of course, you can change maybe sec squared using the square identities, but will it help you to answer the question? Then you'll realize that no, I'm not getting help here. So what do you then do? You move to the following question of trying to make one f of x and the other one f prime of x. So when you try to do that, you'll first start with any. It could be sec. So when you start with sec, if you make sec to be your f of x, can this be f prime of x? No, right? So what do we do? What do we do in that case? We then stop. We check the other one. So we check the other one because of if we make this f of x, this one can't be f prime of x. You understand? When we differentiate this, we can't get this. That's what I'm trying to say. So we check. Okay, if we make this f of x, it could work. However, it's not written in a nice way. So we need to first rewrite it in a nice way, because of if at the same time we make tan squared to be f of x, then it will never get that one. So we have to rewrite it in this following manner. We have to say this one is should be written like this. So this is going to be hyperbolic tan of 3x to the power of 2 multiplied by hyperbolic sec squared of 3x dx. So now we are going to analyze it in this way that I've written. So now we're checking now. If we make hyperbolic tan of 3x to be f of x, can this thing be f prime of x? Yes. However, it's incomplete because of when we differentiate this, we're going to get hyperbolic sec squared of 3x, which we already have. But we shouldn't forget that whenever we're differentiating hyperbolic functions, we should also differentiate the arguments. So the derivative of this argument is 3, but we don't have the 3 there. So you need to make sure that you have 3, and then you cancel out that 3 by multiplying by 1 over 3 outside the integral, so that the 3 and the 3 can cancel out. Makes sense, right? So now, general power rule says that if you have f of x and f prime of x, and this f of x is to the power n, which is not equivalent to -1, then you use general power rule, whereby general power rule states that you just take whatever that you say is your f of x and you add an exponent of 1 to it. So that means this one is going to be hyperbolic tan of 3x to the power what? 3 divided by what? By 3. Of course, we shouldn't forget to take whatever that we have outside the integral with us to our answer. So that means this 1 over 3 that's outside the integral should go with me here to the answer. You understand? So it's going to be this 1 over 3 again, which multiplies that one. At the end of the day, I will have 1 over 9, which is my answer for that question. I hope you got the same thing. All right, this question again. So now, when we check this question, is there something that was differentiated for us to just get this? Yes, because we only have one hyperbolic function here. But then it's confusing because it's not written nicely. So let me first rewrite it in a nice way so that y'all can see what is happening. So here I'm just going to say 1 over x multiplied by hyperbolic cos. So this is going to be a hyperbolic cos of ln of x dx. So when you check the equation that I wrote there, now you can also see that, yeah, indeed, there is something that was ever differentiated for me to get whatever that I have here. You understand? So let's analyze it together then. So remember, we need to always make sure that before we conclude anything, we have the derivative of the argument next to this hyperbolic function. So if our argument in this case is ln of x, natural log of x, and we know that whenever we differentiate the natural log of x, we get what? 1 over x, which is what we have here. So meaning that I have the derivative of the argument and a hyperbolic function. So what do? I ask myself, what is it that was differentiated for me to get positive hyperbolic cos? So it's just hyperbolic sine, right? So that's just hyperbolic sine. So the answer for this, then you just conclude and say this is just hyperbolic sine of that argument, which is ln of x plus c. Then you're done. What more do you want? Makes sense? So yeah, that's just it for that question. I hope you got it because these ones are easy ones. They are easy ones. All right, now we have this one. It looks similar to that one, but they are not the same. This one, it's a little bit tricky if you won't remember some properties or some rules. Okay, look at it. We've got a hyperbolic function which has an argument of a natural log of x dx, and we're supposed to integrate it. So when you check here next to this hyperbolic function, I can't say I have the derivative of this because of the derivative of ln of x, which is our argument for this case, it's 1 over x. And I know that I'm not allowed to put variables. The only things that you can cook here outside the integral. What I'm trying to say here is this before you do it at the end of the day. Since we have hyperbolic sine of ln of x dx, I'm saying that you are not allowed to say that to say or to put 1 over x here for you to force, although that's true, the logic is true that we need to first make sure that there is the derivative of the argument next to these hyperbolic functions. Like, you're not allowed to put anything of variables. So You are not allowed to do this, guys. You are not allowed. It's not allowed, okay? You can only cook numbers. Numbers, even if you can put 1 million, yeah, you are allowed to put million as long as it's a number. But you cannot put a variable, guys. Variables are X, Y, Z, whatever, blah, 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 blah. Those are variables. You are not allowed to put them. Letters, you're not allowed to put letters there unless if that letter is a constant in that question, you understand? Then you can try to cook it. But for this case, X is what we are differentiating with respect to, so you cannot do this, understand? So what does it tell you? It tells you that this method is not working. You need to think of something else for you to be able to integrate this question, you understand? So yeah, I'm just gonna erase this. So you need to remember the definitions of hyperbolic functions, you understand? So the definitions of hyperbolic functions are as follows. So this one of sine is that one. It says that it's e to the power, that argument that we have, so it's going to be e to the power ln of x plus or minus, it's minus, right, for sine. So it's going to be e and minus e to the power negative that argument divided by a 2, then dx, you understand? So now we can see that, okay, I can differentiate this. Yes, I can differentiate this. That's what I'm trying to say. So what are we supposed to do? We are supposed to rewrite it nicely. So I'm going to take the 1 over 2 outside. So I took the 1 over 2 outside. Of course, it might still look like it's complicated, but it's not complicated. It's easy. So I took the 1 over 2 outside the integral. Now what I'm left with is just e to the power ln of x minus e to the power ln of x to the power negative 1. Okay. Okay, so what did I do? You see this negative here, that's here. I took it back to there using the properties of logarithms or the laws of logarithms. You understand? I hope that is not a problem. I hope not. Okay, yeah, since now it's not a problem, then after that it became like this, you understand? So now I need to apply properties of logarithms again. Properties of logarithms says that whenever we have e to the power natural log of f of x here, then the answer for this is just f of x. So what does it mean? It means that whenever you have an exponential function of e to the power natural log of something, then the answer for that is just that natural log. It's just the argument of that natural log, you understand? So if it's x here, then it's going to be x. If it's f of x, it's just going to be that. So what does it mean for this? It means that e to the power ln of x is just going to be equivalent to x. So that's what it means, you understand? So that's what it means. And then minus, so this one, what is it going to be? It's going to be 1 over x, right? Because it's x to the power negative 1. So it's just going to be 1 over x because of x to the power negative 1. X to the power negative 1 is the same as 1 over x. I hope that's not the problem there. All right. Then from here, what are we going to do? We're going to then say, we're going to then conclude that, what is this? We're going to, okay, we can see that now it's easier to integrate. That's what I'm trying to say, basically. Sorry. There's a lot going on in my mind. All right, but anyway, let's push. So whenever we integrate x, what is it going to be? It's just going to be, I don't have to split this, right? I don't have to split and make each term to have its own integral. Yeah, it's easy, right? So this is just going to be 1 over 2 multiplied by x squared over 2 minus 1 over 2 ln of x, then plus c. I hope you all are not confused, but just to avoid confusion, I feel like I need to erase this. I'm sorry if you understand, and I feel like you feel like I'm wasting your time. Sorry, sorry. I just want to make sure that everyone is covered at the end of the day. So what am I doing here? I split it. I made each and every term here to have its own integral because they were sharing it, and then they were also sharing that half, so I gave each its own half, and then now I'm integrating. So this is going to be 1 over 2 x squared over 2, just like this, and then minus what? Minus 1 over 2. Whenever we're integrating 1 over x, what is the answer for that? Is just ln of x, right? I feel like everyone crammed that one. Then plus c. Then tada, you are done. Okay. Yeah, that was it for that question. I hope no one is confused. I hope no one is confused, of course. I hope so. All right, let's see this question. So we have another question here. All right, let's try to be fast now. Finish this. So I hope you are getting these questions there as well. So now we've got 1 over you have 1 over hyperbolic cos squared of 3x, hyperbolic cos squared of 3x. So what can we do here? We can see that we can't say that there is something that was ever differentiated from the hyperbolic function rules, and then we got 1 over cos squared, meaning that we need to rewrite this firstly in a nice way so that we can see what is happening. So what are we gonna do here? We're gonna just say we know that 1 over what? 1 over cos squared is the same as what? As hyperbolic sec squared. So this is the same as hyperbolic sec squared of 3x dx. So it's a reciprocal. Here we have 1, guys. We have 1 here. So 1 over this is a reciprocal of sec squared. So we substituted by that so that we can see what's happening. So but before we make conclusions from here, we first need to make sure that we have the derivative of the argument. So the argument here, it's 3x. Whenever we differentiate 3x, we get what? 3, right? So that's going to be 3, but we didn't have the 3 there. We cancel it out by multiplying by 1 over 3. So then from here, if we have the derivative of the argument and this hyperbolic function, then you ask yourself, what is it that was differentiated for you to get positive hyperbolic sec squared? It's a tan, right? So that's positive hyperbolic tan of that argument. So whatever that you have outside the integral should go with you to the answer, and that's going to be 1 over 3 hyperbolic tan of what? Of 3x plus c. Then you are done. So that's just it. I hope you are getting it. It was easy, right? It was easy. All right, we have this guy now. Let's see what damage we can do to him. All right, so now we've got the integral of e to the power hyperbolic sine inverse of x, all divided by hyperbolic sec of x dx. So what do we do? So we can see that we have an exponential function, and we know that whenever we're integrating an exponential function, we must have the derivative of the exponent. So let's first rewrite this in a nice way so that you all can see what is happening. So here I'm going to write e to the power hyperbolic sine of x multiplied by 1 over hyperbolic sec of x dx. So I know that 1 over hyperbolic sec is the same as what when it comes to the reciprocals? So this is the same as cos, right? Hyperbolic cos. So that's going to be hyperbolic sine of x multiplied by hyperbolic cos of x dx. So what's happening here is that now I need to analyze this integral equation in this following way. Since I'm integrating an exponential function, I need to first make sure that next to this exponential function, I have the what? The derivative of the exponent. So the derivative of this exponent is going to be hyperbolic cos of x, which is what I already have here. So what do I do? If that's the case, then I just conclude that then the answer for this is just going to be e to the power hyperbolic sine of x, then plus c. Ta-da! You're done. That's just it. All right, then now we have this one, this question right here. So what do? We do the same procedure. We're dealing with a hyperbolic function. We ask yourself, is there something that was ever differentiated for us to get hyperbolic tan? Of course, from the formulas there, it's there. It's there. You understand? It's ln of what? Of hyperbolic cos, right? So that's the natural log of that. But before we conclude, we first need to make sure that next to this hyperbolic function tan, we have the derivative of the argument. So the argument is x squared. So we need to first make sure that we have the derivative of x squared. So that's this. So this is hyperbolic of what? So okay, what we're supposed to do is to make sure that next to this hyperbolic tan, we have the derivative of the argument. So the argument is x squared for this case. So here we can see that we have x. So this x is incomplete for it to be fully the derivative of x squared. It's missing a 2 because we know that when we differentiate x squared, we get 2x, right? So we should make sure that here we have 2x. So you're going to put your 2, you cancel out that 2 because of this 2 you are not given, you understand? So you're not trying to change the equation, you're trying to solve this question the way it was given. All right, so now when you have the derivative of the argument and this hyperbolic function, you just ask yourself, what is it that was differentiated for us to get positive hyperbolic tan? So that's just natural log of what? Of hyperbolic cos. So whatever that's outside the integral should go with you to the answer, and that's going to be natural log of what? Of hyperbolic cos of x squared, then plus c. Then you're done. That's just it. Makes sense. It should make sense. It should make sense. It should. It's supposed to. Okay, now we have this question, guys. It's the same thing. It's the repetition. So I've already covered the all types of so who is on? I've covered all the types of how these questions can be given to you or how they can ask you these questions, so yeah. So now we're just cruising. So now we can see we've got this format whereby we've got an exponential function which multiplies the hyperbolic function. What do? We change the hyperbolic function with its definition, okay? So this is going to be e to the power x multiplied by what? E to the power x minus e to the power negative x divided by 2 dx. And then from here, you're going to take the 1 over 2 out. This the 2. This 2, it's 1 over 2. So it's 1 over 2. Hence, I took it out there. So it's going to be from here. Then you multiply this e to the power x, multiply these two terms. So it's going to be e to the power 2x for the first one, minus e to the power 0, which is the same as 1. How did I get 1? E to the power x multiplied by e to the power negative x. The exponents, they add each other to get 0. So it's going to be e to the power 0. E to the power 0 is the same as 1. Hence, I concluded that that is a 1. So that's how I got a 1. All right. Then from here, of course, we can split to avoid mistakes and confusion. So I'm going to make each and every term to have its own integral sign, minus the integral of 1 dx. So now I'm integrating an exponential function of e to the power oh, this one I forgot to give it a 2, guys. Sorry, to give it a 1 over 2. So it's going to be 1 over 2 integral of 1 dx. And then from here, now we analyze it. So since we're integrating an exponential function, we first need to make sure that next to this exponential function, we have what? The derivative of the argument. No, the exponent, sorry. So the derivative of that exponent is just a 2. So since this 2 that I wrote was not there in the equation, I just wrote it. I need to cancel it out by multiplying by 1 over 2 outside the integral, so that the 2 and 2 can take care of each other. And now when I have the derivative of the exponent and an exponential function multiplying each other, then I can conclude that the integral of that is just that exponential function. Of course, I need to take whatever that's outside the integral with me to the answer. So that's going to be 1 over 4, because 1 over 2 multiplied by 1 over 2 multiplied by e to the power 2x minus the integral of 1 is just going to be x. So this is going to be 1 over 2 multiplied by that x, then plus c. Ta-da! You have your answer. So that's how we solve these questions. Yeah. I hope you are getting the concepts. I hope you are getting the concepts. They are easy. All right. We have another question here. Another question, which is the integral of hyperbolic cos of x divided by the square root of 9 9 minus hyperbolic sine squared of x dx. So how do? We need to integrate. we need to do what? Yo, I'm tired. Donate. But guys, let's carry on. We can't be giving up. We've gone far now. Of course, you can drink water there and then come back. All right. So what am I saying? What am I saying there? We need to integrate this thing. So okay, let's analyze it. So when we check this question, is there something that we can say for like from the formulas of hyperbolic functions that, okay, when we integrate sine, for example, we get this fraction? Is it there? No. Okay, then you try to simplify. Okay, if you simplify, can you maybe substitute, maybe change this sine squared to something else, maybe using the square identities? Will it help you in a way that these things can cancel each out and then it gets simplified, J? Like, you understand? It's not gonna be possible. So you check, okay, maybe can I make this or any of these f of x, and then the other one is gonna be f prime of x. You check, if you make the numerator f of x, can this be f prime of x? Definitely a no. If you make this f of x, can this be f prime of x? No. Okay. But since it's a fraction and I know that in fractions, it's possible that this could be one of the inverses. So let's see if I could change, if I could rewrite this in a nice way, in the following nice way. Will it then work? Of course, yes, it's gonna work, because if I can see that, then the numerator is gonna be the derivative of whatever that will be squared there. You understand? So here I'm gonna have, so I can change this 9 to 3 squared if you want. I want to. I changed it because I want to. So hyperbolic sine of x squared dx. Did I do anything to this question? Definitely I haven't done any damage to it. I haven't done any damage to it. So what's left here? So now I'm about to do some damage to it. Now it's dead. Then now I want to destroy it. I want to destroy this question. So yeah. So how are we going to destroy it? Yeah, we're going to destroy it in this following way. If ever I try to use one of the inverses formulas, because I can see I'm dealing with a fraction and this fraction has a square root. So yeah, maybe it could work. So let's see. If ever I let my thing inside the the thing that is squared here, the function that is squared, to be f of x. So if I let hyperbolic sine of x to be f of x, can the numerator be f prime of x? Yes, it can be f prime of x, because of, we know that when we differentiate hyperbolic sine, we get that. So then now the only question that's left is that this structure of having f of x divided by a squared minus f of x squared, it's a structure for which inverse formulas? It's the one of sine, right? Sine inverse. So because of we're having a's, of course we should have 1 over a somewhere, but we know that the one for sine inverse, it doesn't have 1 over a outside, so we should then say this is sine inverse of what? So our f of x is the thing that is squared here, so that's going to be hyperbolic sine of x, hyperbolic sine of x divided by our a being 3, then plus c. So this is our a, guys. Of course, if you already forgot about differentiating inverse hyperbolic function, you can go back to the previous videos. You'll see integration of what? Of inverse trigonometric functions. I've solved a lot of questions and I've explained how to go around them, how to solve them. So it shouldn't be a problem. It shouldn't be a problem. Yeah, it shouldn't be a problem. All right. All right, now we have this question of integral of hyperbolic sec cube of x multiplied by a hyperbolic tan of x dx. So when we check this question, is there something like maybe perhaps chord that was differentiated for us to get sec cube tan this dx? Then no. Then what are we supposed to do? We're supposed to rewrite this thing in a nice way if possible. Otherwise, we cannot be able to differentiate it. So when we check, can we rewrite this thing in a nice way that it could simplify our life, or you understand? So when we check this question, can we maybe substitute, I don't know, change tan to be something else, and then it cancels with sec? I don't know. Do you think like we can do that? And will it help us if we do it? Because of course we can change tan maybe to hyperbolic sine of hyperbolic cos. Like, will it help at the end of the day? Will it help? Because we can't be doing something because of we know that we cannot. You understand? So when we check that, we find that nah, It's not working. However, we can rewrite this nicely. If ever we want to force this one of these to be f of x and the other one be f prime of x, then we'll have to then rewrite this nicely first, because we can see that if if we take one of the hyperbolic sec out here, then we're gonna have something like this. So if we take it out, hyperbolic sec square, or hyperbolic sec of x squared multiplied by hyperbolic sec, of course, multiplied by hyperbolic tan of x dx, like this. So if we make, so you see what I did there, I took one of the sec here, I put it out there so that I'm left with just squared, two of them there. So what's happening now? I'm trying to say that, oh, I saw that if if I make one f of x, then the other one could be f prime of x. Of course, if I've done this. So I see, okay, if I make this f of x, then definitely this can be f prime of x. But if I make hyperbolic sec of x to be my f of x, then this is going to be my f prime of x. So then I just use general power rule, because my n here is equivalent to 2, of course. So general power rule states that you just take whatever thing that you say is your f of x and you add exponent of 1 to it, and then divided by that n plus 1. Then so this is just going to be hyperbolic sec of x, hyperbolic sec of x to the power 3 divided by 3 plus c. Ta-da! You have your answer. Of course, I made a mistake here. Because of what? I'm tired. I'm tired, guys. I'm tired. I'm realizing that when I'm trying to differentiate it in my mind, that I'm getting a negative here in my mind. So what is the mistake, guys? The mistake is well, the mistake is where, guys? The mistake is where I say that when we differentiate this one of okay, when we differentiate sec, guys, what do we get? When you differentiate hyperbolic sec, what do you get, guys? From differential, what is this? Let me also check my formulas fast. We know that when we differentiate hyperbolic sec, we get what? So whenever you differentiate hyperbolic sec, you get negative, right? You get negative hyperbolic sec multiplied by tan. So that means, yeah, this one is not fully the derivative of this, right? It's not fully the derivative of this, because of whenever we differentiate sec, hyperbolic sec to be specific, we get negative hyperbolic sec multiplied by hyperbolic tan. So that means there is a missing negative here. So here I'm supposed to put a negative and cancel out that negative by putting a negative again outside the integral. And then this negative sign goes with me to the answer, and then here I have another negative. Makes sense, right? So yeah, that's the only mistake that I made, a mistake of a sign. So it's maths, guys. You see, even me, I'm getting traumatized. So what can we do, guys? We can't do anything. We can't cry. We just need to understand that maths, it chops. It doesn't care whether you are what or you are who. It chops. All right. So now we have this question here. All right. So this question here, when we analyze it, we are going to realize that we have okay, let's start by analyzing. When we check it, is there something that was differentiated for us to get this complicated quotient or this fraction, it's not really there. You understand? It's yeah, it's yeah, we can't really say it's there from the formulas that we have done already. You understand? Like, ish, but I'm not supposed to say this. What am I supposed to say, kahle kahle? I'm supposed to say that okay, it's there. Okay, let me just say it's there. Okay, when we analyze this thing, we can see that out of all the things, when we check the derivative, okay, it's more like when we have a fraction, you have to always think of also the derivatives of what, of inverses, so that you can see if you can use one of the inverses as the answer for this. So when you check, is there maybe one of the inverses that was used here, was is it one of the inverses that was ever differentiated here for us to get this complicated quotient? No, because of, if we let sine of x, sine hyperbolic sine of x here to be our f of x, then definitely this can't be the derivative of that, of sine, you know. So it's failing. So what does it do? It's telling you that now you need to think of something else. So you check, can I simplify this? You check, but what can I do to simplify this in a way that it can simplify my life? Okay, I know that 1 plus hyperbolic sine squared is what is equivalent to hyperbolic cos squared, right? Hyperbolic squared of x, right? So hyperbolic cos squared of x, hyperbolic cos squared of x. So that's what I'm trying to say. So when we do that, we're gonna realize, okay, actually that works. So this is going to be what? This is going to be a hyperbolic sine of x divided by, so 1 plus sine squared in hyperbolic functions, in the square identities, it is equivalent to hyperbolic cos squared. So hyperbolic cos squared of x dx. Then from here we can just what, use, so there could be two methods. I'm just gonna go with the one for power rule, general power rule. I've explained the other methods for this similar case in previous examples, so you could try them out. They are going to work as well. The one of saying 1 over cos, then 1 over sine over cos, it should work as well, but I'm not gonna do it. I'm gonna just go with general power rule. So I'm just gonna use general power rule here, because if I can see that I've got hyperbolic cos to the power -2. I took that one up. So what did I do? I took the hyperbolic cos upwards there, so that I can apply my general power rule, because I can see that my n there is not equivalent to -1. So I'm supposed to use general power rule. Okay, so when I use my general power rule, I need to first check that if this is my f of x, can this be f prime of x? Yes. So then I just apply general power rule. So general power rule says that whatever thing that you say it's your f of x, you just add an exponent of 1 to the exponent that it already has or have. So it's going to be cos of x to the power what? -2 plus 1. So that's going to be -1, and then divided by -1 plus c. And then this becomes what? -1 over cos of x, or hyperbolic cos of x, plus c. So 1 over hyperbolic cos of x is the same as what? Is the same as sec in terms of reciprocal. So this is going to be negative hyperbolic sec of x plus c. Then tada, you have your answer. So that's that's just it for that question. So what else are we looking at? Yeah, let's see. Let's scroll down. All right, we have this guy. Let's see what we can do to this guy. All right, so on this question, we can see that, okay, we're dealing with a hyperbolic function there. On hyperbolic function, we just need to just make sure that next to that hyperbolic function, we have the derivative of the argument of that hyperbolic function, you know. So, of course, it's not written in a nice way. The first thing first that I can advise is to rewrite this thing firstly in a nice way. So the nice way that you could rewrite this could be this one, whereby you say you put this 1 over root x here, and then you take the cosh on a side. So the hyperbolic cos, you're going to take it on a side so that you can see what's happening. All right. So what's happening here? So here, since we are trying to integrate this exponent, this hyperbolic function, you just need to first make sure that next to it there is the derivative of the argument. So the argument is this angle. So when we differentiate this square root of x, what do we get? We get 1 over 2 square root of x. So we already have 1 over square root of x. The only missing thing is a 2 here underneath. So we're only missing a 2 here. So we have a missing 2 here. So I've put that 2. I need to cancel it out because of it was not there. So to cancel out that 2, I need to multiply it by 2. But if I have the derivative of the argument and this hyperbolic function, then I can just conclude and ask myself, what is it that was differentiated for me to get this positive hyperbolic cos? So it's hyperbolic sine, right? So hyperbolic sine was differentiated for me to get that. So I'm just gonna say what? I'm just gonna say hyperbolic sine of square root of x was differentiated for me to get that answer plus c. Of course, I shouldn't forget that whatever that was outside the integral here should always go with me to the answer. So it's going to be 2 that and then plus c. And then you're done. You got your answer. Makes sense, right? It should make some sense. It should. It should make sense. All right. Yes, another question then. So on this question, we're given that the integral of hyperbolic sec of ln of x multiplied by the hyperbolic tan of ln of x all divided by x dx, then we are supposed to integrate it, of course. So how then supposed to integrate this? So we can see that definitely there is something that was differentiated for us to get hyperbolic sec multiplied by hyperbolic tan. Understand? So what do we then do? We just need to first make sure that we have the derivative of the argument. So of course it's there, but let's rewrite it nicely for y'all to see. So I'm gonna rewrite this question in this following way so that the conclusion could make sense. So this is hyperbolic sec of ln of x multiplied by hyperbolic tan of ln of x. Then what? Then the x here. So what's happening here is that we have what? We have this 2 hyperbolic function and this 1 over x out. So what did I do? I only changed, you see, the way the question was written, I only changed this 1 over x and rewrote it like this. I believe you all can see that this format and this format is the same thing. However, if we wrote it like this, it's clear that this 1 over x is the derivative of this. Right? I understand it makes sense like that, that this 1 over x is the derivative of this argument that we have for these 2 hyperbolic functions. So if we have this argument this derivative of the argument, then we can then ask ourselves, what is it that was differentiated for us to get positive hyperbolic sec multiplied by hyperbolic tan, but it being positive, you understand? So what is it you ask yourself there? So when you ask yourself, you'll realize that, okay, the one for that one, if it's positive, then it's going to be even my throat is starting to be dry right now. Okay, it's the one of negative, right? It's the one of negative. So if it's positive here, if we have positive sec tan, then we know that the one that was differentiated, it has to be the one for negative. So it's negative hyperbolic sec. So it's going to be negative hyperbolic sec of what? Of that argument of ln of x. Then plus c. Then you're down. Ta-da! You have your answer. Okay. All right, few questions to go. All right, we have this one again. So this is, I've already told you that this one, we don't have it in our formulas, right? So I told you that I've even told you the procedure to solve it, right? I hope you still remember it. So whenever we're integrating hyperbolic cosec of x, what do? We first change it to its equivalence when it comes to the reciprocals, right? So the first step is to change it to its reciprocal. So this is the same as 1 over hyperbolic sine, right? So this is going to be the same as 1 over hyperbolic sine of x. Hyperbolic sine of x dx. And then the second step is what? Is to multiply by 1. So the 1 is to be whatever thing that you have on the denominator, you say itself divided by itself. So that's going to be this one. So this is going to be 1 over x multiplied by hyperbolic sine of x divided by hyperbolic sine of x dx, like this. Oh, okay. Yeah, dx like this. So you can see that is like that. So from here, you just need to multiply the numerator and the numerator, denominator and the denominator. So at the end of the day, when we do that, we are going to get hyperbolic sine of x divided by what? Hyperbolic sine squared of what? Of x dx, like this. You understand? Yes. Then from there we said we change the thing that we have on our denominator. For this case, it's hyperbolic sine squared of x. We changed it to its equivalence when it comes to square identities. You understand? So according to square identities, we are going to get what? We are going to get the following. Okay. We are going to get, right, so let me write that numerator the way it is, divided by, so that one is going to be cos, hyperbolic cos squared of x minus 1 dx. When we use square identities, guys, it is equivalent to this in hyperbolic functions. You understand? Then from there, what do we then do? We can see that we need to first take out 1 as a common factor, or negative 1, basically, to be specific. Negative 1 as our common factor there. -1 as our common factor on our denominator there. So I'm going to take -1 as my common factor. Okay, so I'm going to take -1 as my common factor on my denominator like this. So it will become, I'm thinking like this because of I already know the procedure since I explained the procedure, guys, at the beginning of the video. I told you that the one for hyperbolic sec and the one for hyperbolic cos, you use the same procedure, and then you're gonna have one of the inverses at the end of the basis. So I can see that I don't have this on my formulas, so I need to use what? Do the following. Take out negative as a common factor. So when I take out negative, there's a common factor. I'll have 1 minus hyperbolic cos of x. Okay, it's squared, of course. Then dx here. Then I can take out that negative out. The negative that's outside, I can take it out. I mean, the negative that's on the denominator there, I took it out, and then now what I'm doing now is that hyperbolic sine of x divided by 1 minus hyperbolic cos of x squared dx. So here what you need to do is that you need to now analyze it using the formulas for inverses, because the procedure is already given, guys. I've already given you the procedure. That the procedure, it's always gonna be like this whenever we are differentiating, whenever we're integrating this one of cosec and the one for hyperbolic sec. So then now you'll realize, okay, this format whereby we let cos to be our f of x, and then the numerator becomes our f prime of x, and then it's like this, like the format is like this. We have 1 minus f of x squared, then we have f prime of x on our numerator. Then it's a hyperbolic cot inverse, right? So that's going to be cot inverse. You understand? Hyperbolic cot inverse. That's what I'm trying to say. So this is going to be negative hyperbolic cot. So this is going to be negative hyperbolic cot inverse hyperbolic cot inverse hyperbolic cot inverse hyperbolic cot of what? Of f of x, which is cos there for this case. So it's going to be cos of x and then plus c. Then you're done with that question. Make sense? It should make sense. It should make sense. So yeah, that was it for that question. Let's quickly see what we can do to this other one. So now we have I'm tired. Okay, now we have this question here. Let's just hang in there, have some strength, and then yeah. Tired, man. Oh. Why did I start these videos? Okay, now we've got this fraction integral of hyperbolic sec squared of x divided by 1 minus 2 hyperbolic tan of x dx. So we can see that definitely there was nothing that was ever differentiated for us to get what? There was nothing that was ever differentiated for us to get this complicated fraction. I'm sorry guys, I'm just, my mind just like sometimes it flies away and I'm here and I'm tired. All right, so I'm saying that from your formulas you can't say that something was differentiated for you to get this big fraction, you understand? So what do you do? You then try to see if you can simplify this. So you check if maybe you can change sec squared there. Will it help you in a way that maybe certain things can cancel out, and then you conclude that okay, this was differentiated for us to get this? Then no. What do you then do? The second question that you ask yourself is that, can I make one f of x and the other one be f prime of x? So if in this question you make sec squared, hyperbolic sec squared of x to be your f of x, can then this denominator be f prime of x? Definitely, and no, it cannot be the derivative of that. So what do we then do? We try the other one. So we try to make the denominator f of x. So when we make this denominator our f of x, can the numerator be f prime of x? Yes, but it's incomplete because of, we know that when we differentiate 1 minus 2 hyperbolic tan of x, we get negative 2 hyperbolic sec squared of x, right? So that means it's working when we use our denominator. However, that numerator is incomplete for it to be fully the derivative of the denominator. So what do we then do? We rewrite this thing nicely. So I'm gonna say 1 minus 2 hyperbolic tan of x dx, and then on my numerator here, what am I gonna do? I'm gonna say that I'm gonna copy sec squared. So I'm gonna copy sec hyperbolic sec squared of x, and then I know that when I differentiate this, I get minus 2 hyperbolic sec squared of x, right? So that means I am missing a minus 2 here, but then I didn't have this minus 2, so I need to cancel it out by putting negative 1 over 2 outside the integral, right? So now I've analyzed it, that I have my f of x in my denominator, and that f of x has an exponent of 1, and then my numerator becomes what? The f prime of x when I try to differentiate this. So meaning that I am allowed to use general power rule because of my n here is equivalent to 1 and it's in the denominator. So then from here I conclude that negative, so I take the negative 1 over 2 with me to the answer, so negative 1 over 2. So whenever, so general power rule here is gonna be natural log of what? Of 1 minus 2 hyperbolic tan of x, and then plus c. Natural log just says that you take your f of x, you put it inside the line, so the f of x becomes the argument for your line. So that's just a general log rule. I hope no one is confused. I really hope that you cannot afford to be confused. It's very expensive. If you are getting confused, you must be very rich. You must be very rich. All right. Anyway, we have this following question here. Okay. Evaluate the following definite integrals. So now we're trying to solve some definite integrals. So let's see how we can do that. So we can see that the first question that we're given, that it's hyperbolic sec of x, sec of 1 over x multiplied by hyperbolic cot of 1 over x, all divided by x squared, right? So we can see that our arguments for this case, we have 1 over x, and it's just 1 over x. That's just the argument that we are dealing with. It's just 1 over x, you know. So we need to rewrite this thing firstly in a nice way, because we can see that definitely there was something that was differentiated for us to get cosec cot, right? So let's first rewrite this in this following format so that it can make sense. So let's take okay, 1 over x squared, 1 over x squared like this, multiplied by hyperbolic cosec. So hyperbolic cosec of 1 over x multiplied by hyperbolic cot of 1 over x dx like this. So you can see that definitely there was something that was differentiated, I mean, for us to get cosec and cot, right? But before we conclude that, we need to first make sure that there is the derivative of the argument next to these three hyperbolic functions. So when we differentiate 1 over x, what do we get? So when we differentiate 1 over x, so the x of 1 over x the same as x to the power negative 1. When we differentiate it, we get negative 1 over x squared, you understand? Or negative 1 multiplied by x to the power negative 2 to be specific, which is the same as 1 over negative 1 over x squared, you understand? So that is the answer. So here, when we check, we only have 1 over x squared. So what's missing is the negative sign. So the negative sign is missing here. So I'm going to put the negative sign here and then cancel out that negative sign by putting out a negative outside the integral. Makes sense? So then from here, I ask myself, what is it that was differentiated for me to get positive cosec, hyperbolic cosec of x, hyperbolic cosec multiplied by hyperbolic cot? So that's what I ask yourself. So that's what we ask ourselves, you understand? So whenever we differentiate and we get it being positive, we know that it is negative hyperbolic cosec that was differentiated, you know. So the answer for this is just gonna be negative hyperbolic cosec of what? Of that argument plus c. But I shouldn't forget whatever that's outside the integral to come with me to the answer. So this negative should multiply this other negative here. So this one goes there. And then this other negative is coming from me asking myself that what is it that was differentiated for me to get positive hyperbolic cosec multiplied by cot, you know. So I know that if I got it as positive, then that means it is the negative one that was differentiated, and then I take the negative out, the negative that was outside the integral with me to the answer. At the end of the day, the answer for this is just going to be, oh, it's a definite integral that I'm dealing with. Sorry guys, there is not supposed to be a plus c there. We're supposed to substitute our our limits. So sorry, here it's going to be 2 1. Sorry, I must have forgotten that. So negative and negative, they multiply each other, so we'll get a positive. So at the end of the day, here we'll just get hyperbolic cosec of 1 over x, and then the limits being 2 and 1. So we need to substitute these limits in our calculator. So we know that in our calculator we don't have hyperbolic cosec, right? So what do? We try to rewrite hyperbolic cosec with its equivalence when it comes to reciprocal. So this is going to be 1 over hyperbolic sine of what? Of 1 over x, and then we put our limits being 2 and 1. Then from there we substitute the limit. So it is going to be 1 over. So it's going to be 1 over hyperbolic sine of 1 over 2. We start with the upper limit minus 1 over hyperbolic sine of 1 over 1. Then we try to do that with our calculator. Let's see what do we get. So I'm punching now in my calculator 1 over hyperbolic sine. So it's going to be 1 over 2 minus 1 over hyperbolic sine of what? Of 1. You should be able to get something like 1,068. 1,068. So that should be your answer. So yeah, anyway, to punch in the calculator, you need to punch hyperbolic things in the calculator. You press HYP, which is underneath x squared, the under x squared. You will see hype if you are using the casual calculator. If you are using casual fx what? Fx 991 za plus 2. za plus 2. Yeah. If you're using this calculator, then you should be able to find hype there. Hype. Yeah, HYP. So if you press that HYP, it will give you options of hyperbolic functions. So then you'll press them there. So yeah, that's how you get to this answer that I have there. All right, let's see if we can solve another question here quickly. So we have another question here, which is like this. So what do we do to this question? We try to solve it, this hyperbolic function. So we can see that we have hyperbolic cos x squared, right? So we know that there is something that was differentiated for us to get hyperbolic cos x squared, right? So what do we then do? We then just first make sure that next to this hyperbolic function, we have the derivative of the argument. So the argument here, it's x squared over 2. So this is the argument as a whole. This thing of x squared over 2, it's our argument. So we need to make sure that next to it, we've got the derivative of next to this hyperbolic function with the derivative of the argument. So we only have x there, so meaning that it's incomplete because of, is it incomplete or it's complete? It's complete, right? Because when we differentiate 2x, x squared over 2, we're going to get 2x divided by 2. 2x divided by 2 is just x. So it's complete. Yeah, it's complete, guys. So what do we then do? We just say, okay, we have a hyperbolic function and the derivative of the argument. So what do we then do? We just ask ourselves, what is it that was differentiated for us to get positive hyperbolic cos x squared of that argument? So the positive one, we know that it's what? It's negative what? Negative hyperbolic cot of that argument. So the answer for this is just negative hyperbolic cot of what? Of that argument that we're dealing with, x squared over 2. Then you put your limits being 2 and negative 1. Then from there, we are going to substitute our limits. So from there, we're going to substitute our limits being what and what? Our limits being 2 and negative 1. But we know that on our calculator, the calculator that I'm using, basically, because now you might argue with me and say, but now I can substitute hyperbolic cot in my calculator. So in the calculator that I'm using, casual fx 991 za plus 2, you can't be able to substitute that one. So what we're gonna do is to first substitute this into its equivalence. So we're going to change it to its equivalence when it comes to what is that? Reciprocal. So this is going to be hyperbolic tan of what? X squared over 2. Then you put your limits being 2 and -1. Then you substitute the limits here. So now we're going to substitute the limit is going to be -1 over hyperbolic tan of what? Hyperbolic tan of 2 squared. So it's going to be 2 squared over 2. 2 squared over 2 minus again. So it's going to be minus what? Minus 1 over hyperbolic tan of -1 squared over 2. Then you close, of course. Then now we try to find the answer from there. So let's see when you press the calculator. So I'm gonna press now. I'm pressing right now on my calculator. You can also be practicing to punch these things in your calculator as well. So you're gonna press hype there. You press 3, which is that one. So 4 over 2 is the same as 2, and then plus 1 over hyperbolic tan again of what? Of 0.5. Then you press on your calculator. You should be able to get 1,127 as your answer. So this should be your final answer, provided that you didn't make a mistake. I didn't make a mistake. So yeah. So that's how you get the answer. So that's just it. I hope you got it. So yeah, let's see if we can solve a few more and then we conclude. So just 4 questions and then we'll be done. 4 questions, then we will be done. So okay, yes, this question, this one, we're already done with it. We know that hyperbolic cos of x squared minus hyperbolic sine squared, it's a what? It's a square identity, right? So this is just equivalent to 1. So we don't have to think more here. From the get-go, we can already see. I hope you also saw that. Otherwise, we're going to have a big matata. All right, so this is just 1 dx. This minus this is the same as 1. So now to integrate 1, what do we get? We get, when we integrate 1, we just get x, right? With respect to x, we get x. And then we put our limits. And then what's going to happen here is that we're going to get pi minus 0. And then our answer is just going to be pi, right? And then ta-da, you have your answer. Make sense? Yeah, it should make some sense. It should. All right, so now we have this question here, square root of this. Okay, so now we've got square root of 1 plus hyperbolic sine squared of x over 10 dx. Okay, it looks complicated, but it's very easy. All right, we can see that already there is nothing that was ever differentiated for us to get this square root of this thing that looks like it's complicated, but it's not. So what do we then do? We try to see if we can simplify the given integral. But so when we check it, we can see that, okay, 1 plus hyperbolic sine squared is the same as hyperbolic cos squared, right? So that means here the thing that we can go with is that we can put our limit there. We take our 2, we say square root of what? Of cos, hyperbolic cos squared of x over 10. And then we put our dx there. So Hyperbolic cos squared is going to cancel out this radical sign, right? So at the end of the day, we'll only be left with, okay, I can also take these two outside the integral because I can see it's causing some traffic. So I'll only be left with hyperbolic cos of what? Of x over 10 here inside. And then here I have what? I've got my dx. So the radical sign chopped this squared, right? So then this 2, I took it out. There it is. So now I only have one hyperbolic functions to integrate that. The procedure is the same. It didn't change. What we need to first make sure is that next to this hyperbolic function, we have the derivative of the argument. So the argument is x over 10. So when we differentiate x over 10, what do we get? We get 1 over 10, right? So we get 1 over 10. So I need to make sure that here I have 1 over 10. But because of this 1 over 10, I didn't have it in my equation. I'm just putting it so that I can be able to integrate. Then I need to cancel it out by multiplying by what? By 10 here outside the integral. You understand? So that the 10 and the 10 can cancel out. So now when I have the derivative of the argument and this hyperbolic function, then I just ask myself, what is it that was differentiated for me to get what? To get positive hyperbolic cos. So I know that is just what? It's just the hyperbolic sign, right? So this is just going to be hyperbolic sign. A hyperbolic sign of what? Of x over 10. So this is going to be hyperbolic sign of x over 10. That was differentiated. But I shouldn't forget to take whatever that's outside the integral to go with me to the answer. So here I should write my 20 because 2 times 10 is a 20. Then I put my limits 10 and what? And 0. 10 and 0. Just like that. Makes sense, right? So yeah, it should make some sense. It should make sense there. And then from here, I'm going to get this one. So we're going to substitute the limits. That's what I'm trying to say. So we're going to substitute the limits here. We are going to substitute the limits. Okay. So let's substitute the limits. So here it's going to be 20 multiplied by hyperbolic sign of what? Of 10 over 10. 10 over 10 minus 20 hyperbolic sign of 0 over 10. Then let's see what answer we are going to get. So just a second, I'm also pressing on my calculator. Please be patient with me. So just a second. Hype 1 minus 20 hyperbolic function of what? Of 0. So yeah, you need to get 23,504 as your answer there. So yeah, then that answer will be correct, provided that it didn't make a mistake. Yeah, you should have gotten what I got there. So yeah, that's just it for that question. Yeah, that's just it for that question, guys. There is nothing else that we can worry about. Okay. All right, so let's see this second last question, then we are done. So we have been solving we have been solving problems. All right, we've got this question now, the integral of 1. So we've got the integral of 1 divided by this. So this question could be done in two ways. I don't know. Should I do 2 or 1? Now I should analyze your brain there and make some guesses. And I'm thinking that you're saying that man, you have done enough now for this video. Yeah, you can just do one, right? Yeah, I think that's what you're saying. So let's see which one can I use there, because since it's two methods. Okay, so this one we can use the method of multiplying by what? By 1 on both sides. So we're going to multiply we're going to multiply by 1. Yeah, let's go with that one of 1. The other one, I feel like it's tricky. So at least the 1 is similar to what we did in the previous video of differentiating trigonometric functions. I say that when we have this shape, we multiply by Pythagorean conjugate. You understand? So we're gonna do the same procedure there. So we're gonna multiply by that 1 plus cosh on both the numerator and the numerator. Basically, we're multiplying by 1. That's what I'm trying to say. So 1 minus hyperbolic cos of x. So what we're going to do is to multiply by 1. But that 1 should be 1 plus hyperbolic cos. I don't know if it will be correct for me to say it's a Pythagorean conjugate, but it's not. But let's just abuse maths for now, for the sake of you to understand. We are multiplying by the conjugate of this. So 1 plus, it's a conjugate as long as it opposes the sign. So we're multiplying by the conjugate of that denominator. Yeah, so that's what I'm trying to say. Hyperbolic cosh of x divided by 1 plus cosh of x, and then here there is dx. You understand? So then from here we multiply the numerator and the numerator. So at the end of the day, we'll get the following: 1 minus 1. There we're gonna get 1 plus hyperbolic cos of x divided by this thing, this numerator multiplying that numerator. Will have to get 1 minus hyperbolic cos squared of x, right? Dx, like this. So 1 minus hyperbolic cos squared of x is equivalent to what when it comes to square identities? It is equivalent to the following. So this is going to be 1 plus hyperbolic cos of x divided by what? Divided by this negative hyperbolic sine squared of x dx. So what did I do? I changed 1 minus hyperbolic cos squared of x to its equivalence when it comes to square identities. So you know the square identities, guys, those are basics. So I changed 1 minus that into its equivalence when it comes to that, so it became this. You understand? So now I'm going to split so that each have its own denominator. You understand? So I'm going to split them. So each is going to have its own denominator. At the end of the day, I'm gonna have 1 minus 1. So it's gonna be minus 1 over hyperbolic sine squared of x minus what? Minus, or maybe I can all let me just split it like this, is the same. Minus what? Minus hyperbolic cos of x divided by hyperbolic sine squared. So here I'll just use the general power rule is good. I'll just use general power rule after this. It's okay. Hyperbolic sine squared of x, and then you close here, you close, and then you're gonna have dx. So everything here is integrated with respect to x. Okay, And then from here, what are we going to do then? What we are going to do then is just to make sure that we change these things to their equivalence when it comes to reciprocals. So it's going to be 1, -1. So this one is the same as negative what? Negative 1 over sine when it comes to reciprocal is the same as negative cosec, right? CSCH squared of x. Then yeah, then like that. And then minus what? So here I can I'm gonna use I just want to rewrite this in a way that general power rule is gonna work, because I can see that it should work. So I'm gonna take the hyperbolic sign upwards, so this is going to be hyperbolic sign squared of x. Hey, when I take the squared outside there, and then everything here is inside the brackets and is integrated with respect to x. Okay, so now we're going to integrate them respectively. So I don't know, one could say I want to split, or one could say I don't have to split, but it's the same thing at the end of the day. Splitting or not splitting is the same thing. Should I split or not? I shouldn't split, right? I'm tired, guys. I'm just tired, sorry, ne? I'm just tired of it. Yo. But one thing left, one example left. So let's hang in there, have some energy, drink some water, pause the video, go jog, do some push-ups there, and then come back to the video. You push this maths thing, because at the end of the day, you need to pass, and being tired is not an excuse, that you should take. Okay, so what are you gonna do here is that you're gonna integrate this one and then integrate that one, and then we put the limits. So to integrate this one, we can see that, okay, definitely there was something that was integrated for us to get hyperbolic cosec squared, right? So we just need to ask ourselves, what is it that was differentiated for us to get negative hyperbolic cosec squared of x? What is it that was differentiated for us to get negative hyperbolic cosec squared? You understand? So when you try to remember that, you'll realize that, okay, the one that was differentiated for us to get negative hyperbolic cosec squared, it's positive hyperbolic cot, right? So that means the answer for this is positive hyperbolic cot of x. And then we analyze. So, oh, this one I even made a mistake. I said this is negative, is positive 2. And I said I'm taking this one up. So it was supposed to be negative 2. I'm very, very sorry for that. I'm very, very, very sorry. Mistakes happen. At least you just need to make sure that you see them in time. You understand? So yeah, that's a negative 2 there. Makes sense? Okay. So I can see here I'm supposed to use general power rule, because of, if I make hyperbolic sign of x to be my f of x, then this is going to be f prime of x. So hyperbolic sign of x multiplied by this, and then I'm gonna use just general power rule, because of this is f prime of x and this is f of x to the power n, which is not equivalent to -1, so I'm allowed to use general power rule. So I'm gonna take this negative with me to the answer. So I'm gonna have this negative with me to the answer, and then I just take my f of x, which is this one. So this is going to be hyperbolic sign of x to the power -2 plus 1, that's a -1, divided by what? A -1. Then I put my limits, 1 and -1. So at the end of the day, this negative and negative will cancel out, and then we'll have 1 over hyperbolic sign, right? So also let's change this one to hyperbolic tan. So this one is going to be 1 over hyperbolic tan of x. I'm changing it to these ones because of, in the calculator I only have hyperbolic tan, hyperbolic sine, and hyperbolic cos. So yeah, let's leave it in this way of hyperbolic sines and tans. So This one is just going to be, oh, this one we said is gonna be plus hyperbolic sine of x, and then you put the limits 1 and minus 1, just like that. Yeah, just like that. So now we just need to put the limits. Okay, so now we're going to substitute our limits. We should be able to get something like what I'm gonna get when I punch my calculator. For now, I'm just substituting here in my calculations. Plus, we're starting with the upper limit, right? So this is going to be a hyperbolic sine of 1 minus what 1 divided by hyperbolic tan of -1 plus 1 over hyperbolic sine of -1. Then you close. Then we try to find out with our calculator what the answer is gonna be. So yeah, I'm trying to punch right now in my calculator. All I need from you is just patience. All I need from you is just patience, because I don't practice, guys. I just do these questions. I believe that I know how to solve. That's why sometimes I make mistakes, because I didn't practice, I just got into this question. Now I'm doing a video. So at least if I practiced before, I would then say I remember that, okay, this answer was this, but then now I don't remember because of I didn't practice. You see, you should practice, guys. You shouldn't be like me. I don't understand myself why I'm like this. Okay, 1 minus hyperbolic tan of, yeah. All right, after pressing on your calculator, you should be able to get something like 4,328 as your answer for that. So then it will be correct like that. Makes sense, right? So yeah, it should make some sense. So let's just do one last question, then we close it for today or for now. Then we'll meet again on the next video. Still a lot to be covered. Okay, what do we have right now? We've got the integral of 1 divided by hyperbolic cos squared. Let's take you down. All right, we've got integral of 1 divided by hyperbolic cos x squared, hyperbolic cos squared of x, that hyperbolic tan squared plus 3 dx. So what are we supposed to do? Okay, we can see that there is nothing that was differentiated for us to get this thing. So we need to first think of rewriting it nicely. And then, if possible, we then think of simplifying. So yeah, let's see. So we can rewrite it nicely first by saying that, by rewriting it in this way. Look at it when we write it in when we rewrite it nicely. Also, here it's just the typing errors. There's supposed to be x here, so it's hyperbolic tan squared of x. You understand? So it's just the typing error. No, you shouldn't be scared. So what I'm gonna do here is just to take the hyperbolic cos squared. I'm gonna take it up, and then I'll end up having the following. I'll end up having hyperbolic tan squared of x plus 3 and then dx. So did you see what I did? I only took out this one upwards. I took it up and then it became 1 over this. You understand? And then I left these ones down here, because I can already see that this one, it's gonna be one of the inverses, right? You all can see, right? I hope so. I hope so. I hope so. Okay, now let's see if you change this one to its equivalence when it comes to reciprocals, then how much is it gonna be? So now we're still rewriting this thing nicely. So this is 1 0. 1 over cosh is the same as hyperbolic sec, right? So this is going to be hyperbolic sec squared of x, just like that, divided by okay, I can see that this is going to be the inverses, guys. Yo, I'm very sorry for my insights. Sometimes it makes me not to explain more the fact that I can already see. I jump the steps of explaining. Okay, let's rewrite this 3 in this format of root 3 squared and then dx. So what did I do? I saw that from the get-go here, from this step, that okay, if I can change this one to be hyperbolic sec squared, then I know that if I let the denominator to be f of x, the whole denominator to be f of x, then that's gonna be fail to become f prime of x. However, if I let just hyperbolic tan of x to be f of x, then the denominator can be f prime of x. Hence, I rewrote everything in this format, you know. So when we have this one of okay, we can see that is one of the inverses. So when we have this format of f prime of x divided by f of x squared plus a squared, it's the one of what? Is the one of tan, right? So we've got tan inverse here. We've got tan inverse. So we've got tan inverse of what? So it's going to be 1 over a. So it's going to be 1 over root 3. So it's going to be 1 over root 3. Tan inverse of what? Tan inverse of our hyperbolic function, which is hyperbolic tan of x. Then we put our limits 1 and 0. Yeah, 1 and 0. Makes sense, right? Yeah, it should make some sense. Oh, hyperbolic, this is over a. Sorry, now I'm making mistakes now, but it's the last question, guys. I hope it makes sense. Hyperbolic tan of x divided by root 3. Root 3 is our a, guys. We have done inverses for investing, guys. If you forgot, you can quickly just go back after this video. You revise inverses. I've explained inverses nicely in the other videos. So yeah, so this is how it's gonna be, I believe. And then from there, what do we then do? We just then substitute our limits, right? So when to substitute our limits, it should be easy. It's just gonna be 1 over root 3 multiplied by tan inverse. One more thing is just to make sure that you have your calculator in radians, because now you're dealing with a trigonometric function, inverse trig function. So you need to make sure that your calculator is in radians, I think, for you to be able to get the correct answer. So now I'm just substituting. This is going to be hyperbolic tan of 1 divided by square root of 3 minus 1 over square root of 3 hyperbolic tan inverse of inverse in tan inverse of hyperbolic tan of 0 of hyperbolic tan of 0. This tan and hyperbolic, now to say all of them at once, now inkinga ke le over 3. Then now let's see. I'm gonna punch this on my calculator. Let's see what I'm gonna get. Okay. So 1 over square root of 3. 1 over square root of 3 tan inverse shift tan inverse of tan. Oh, this one to press it is not nice, but I'm pressing on my calculator, guys. Please be patient with me. I'll be done just now. 1 over root 3 shift tan inverse of hyperbolic tan of what? Of 0 over root 3. You close. Okay. Yeah, you should be able to get 0 0.239 as your final answer. So yeah, that is the correct answer for that question. So thank you for watching. I'll catch you on the next video. Take care.